especially in old cities like Boston, Chicago, Seattle, all those cities, because if you were to look at like the history of New York, for example, and you do like phase one investigations, you go back to like the 1800s, wherever you can get maps, those fire maps, all these different industries, dentists back in the day would dump in their backyard, nail salons, like you name it, and that's a very common thing across really any city. When you deal with organic compounds, they're a different beast entirely. Those things are very difficult to monitor because they're like amoebas, and they literally move like that. It's very hard to predict where they're going to transfer next. Very much influenced by water movement and air movement, and they kind of like act like globules, because globules like mercury can kind of separate and disperse in various ways. So a lot of times it's even hard to figure out how contaminated a place is, because sometimes you'll be monitoring and you'll hit a plume here, and there's one sitting silent that's hard to discover, and you'll find it like 10 years later because it will have moved, because there'll be a new infiltration initiated somewhere. Like a lot of times they'll put like heating tanks in situ for those soils. That remove that. Yep. So you're basically initiating all those volatile compounds that have boiling points that are like at 100 versus ones that have them at 300. They heat the soils enough that they volatilize, and they capture those volatiles, distill them, and then move with that. Those contaminants are the kind that they're so complicated and so intense that you don't even want to start exposing them, because the problem is so crazy. And the moment you touch it and you move it, you're dealing with another beast entirely. So many of the cleanup efforts are literally just to cap it as much as possible, and then put in. It's now law to put in those vapor barriers. So it's like a 3-floor basement. The first floor catches the vapors, the second floor, and the third floor, and then they blow these vapors out of the building, so there's no way these vapors can enter into the building. They've done several studies in many cities where they literally just take soil samples at the edge of the house, middle of the yard, and then 200 feet away, and it's always highest at the house, and furthest you go away, but the same coincides with roadways. Higher near the roadway, less than when you go away from them.
Do you have some idea about why heavy metals persist in soil?
With the charges, with its stick.
A lot of them are cations. A lot of soil colloids are. What kind of charge? Negative. They claim right there. And those soil particles, those clays and humus particles, are microscopic. And if they're exposed to the surface and they're dry and the wind blows, they're dust. And they can be strewn about everywhere. And that's how beds are often recontaminated. Microscopic dust particles, you can't see.
Every plant has a specific affinity to certain nutrients and certain metals. And some plants will like some metals, and some plants will hate those metals. So if you have a persistence of a certain plant that, likes copper or zinc, then you might hypothesize that that's abundant in the soil. We can start there. As for looking at a site and understanding what is growing there, and then figuring out what's happening in the soil, the microbes come into play there. And I know that they're starting, BC is really seriously starting a research project where they explore the microbial diversity of the soil, and then try and understand the soil's preference then to harbor invasives versus natives or different types of plants. And they're realizing more and more that it all has to do with the microbes. It's kind of like your gut. It's up to the microbes to decide whether or not you're going to take up the nutrients out of the food that you eat. Same thing here. It has all to do with them.
Organisms are the active agents of decomposition. If we have this decaying organic matter and these nutrients that can be released from that, it's organisms fulfilling that role. Right? So they are cycling nutrients, making these nutrients available for new forms of life. 50 kilometers of mycelium, 500s of species, 100 billion different bacteria, 500 meters of different roots, tens of species, a few mammals, hundreds of species of algae, 100,000 and hundreds of species of protozoa, 10,000 nematodes, and maybe 5,000 insects, arachnids, mollusks, and worms. That's all in your handful.
When we talk about ions and we talk about cation exchange capacity, we're talking about ions because that is the form of the element that the plant takes up. It only deals with ions. It doesn't deal with molecules, it deals only with ions. Charged ions. They have to be charged and they have to be an ion.
But organisms can break down chemicals, but these are, again, mostly organic chemicals that organisms can break down. So they can decompose and an organic molecule into carbon dioxide and water. We call this bioremediation. Again, for nutrients, all these different plant nutrients, for them to be available for a plant, they have to be dissolved in the soil water. So, as you see here, I really like this diagram that shows that phosphorus, we know, is only available in this neutral range. It's not available at high pHs, it's not available at low pHs, and because at high pH it'll bond with calcium, at low with iron or aluminum. Right? But most of the nutrients are available in the neutral pH, and they get less available at the extremes. So to know your nutrient levels without knowing your pH doesn't make a lot of sense.
So we, people who were in charge of the microbiology, went in first, and we would take a little bit of soil in a test tube from each one of the horizons. We found that the most abundant taxa in our sites were at the phyla level. And then again, we could go finer, but this is summary. Acetobacteria were the most abundant, followed by proteobacteria, which doesn't follow the usual canon. We found a phylum called 83. It has never been seen or cultivated, so we know it exists because of DNA, but we don't know how it looks like or what it does, so that's why it has a code and not a real name. And followed by actinobacteria. Now, if you broke down those soils in between the natural ones and the human-altered ones, then in the natural ones, acetobacteria were the most abundant, followed by the mysterious 83, followed by those two. And then in the human-altered ones, proteobacteria, acetobacteria, and actinobacteria were the most abundant. So what we found is that in the natural ones, those kind of 83 phylum orders kind of become more abundant as you go deeper. So here, left to right is deeper in the soil, and then this is just the abundance. So as you go deeper in each one of the soils, then those orders become a little bit more abundant. That didn't happen in the human-altered ones. If you compare the diversity, what we found in natural ones is that you had very high diversity on top, where most of the organic matter and most of the biological activity is going on. And then in the human ones, we actually found almost as much high diversity, which initially I was expecting a little bit less diversity because I was expecting more contaminants in the soil and affecting bacteria. It doesn't matter. What matters is that because they have been altered, when you have an altered ecosystem, the diversity tends to be a little bit higher than you have a stable ecosystem, and that's what happened in the soil. So diversity is very high, comparable to those in the naturally deposited material soils. pH kind of determines what kind of bacterial community you have. Now, it goes both ways, right? pH affects the bacterial community, and the bacterial community can affect pH. But so far, this is the main abiotic factor that we found correlated with how those communities are being found.
We had some that are more anthropogenic or human affected, and those tend to be like 7 to 8, as Tatiana said. But the ones that are less, like those in parts, are more like 5 and 6, so a little bit on the other side in New York City.
But if you're in a humid region, you have more precipitation than evapotranspiration. So the more precipitation you have, the more downward movement of water through the profile, the more you'll have cations moving, anions moving down the profile, acids being added. Your soils tend to be more acidic.
Yeah, the more you break down minerals, the more ions will release. So in humid regions, you just have more of that. Whereas in temperate climates, you have less weather and less ion release.
And when it's arid, you have water moving up through the profile, and you have non-acid cations staying there and making it less acidic. In general, if you're in a humid area, you might have natural acidic soils, but in an urban environment, we tend to have more basic soils. And this can be measured quickly, which you guys will do today.
About 30 seconds of just waiting.
At this point, drop in 2 pills of Flock-X in the tube. I've done it many times, it doesn't matter what order you put in, whether you do it first, later. So you can put your 2 Flock-X pills and water into your tube.
We're going to fill till 30. And put in 2
The Flock-X
Flock-X.
is orange. Now, if you guys were to do this experiment at home, it's important that you use deionized water. You want water that doesn't have particles in it like the tap water would, because that could influence your readings.
2 in there,
30 mils.
water,
Yep.
shake.
And you can also put in your soil at this point. But remember to squeeze the bulb first, then dip in your soil, and don't go all the way to the bottom. Make sure you try and extract the soil solution without disturbing the soil.
So what, how are you connected with that site?
I live a block from it. Yeah, so I'm kind of nervous all the time about kind of like the airborne stuff that's flying in through my window.
Yeah.
If you're gonna use
And I'm so low on nitrogen.
I think
That makes me worry.
so that one
I think I have medium. Yeah, I have no nitrogen.
borderline high, but I would call it medium. 'Cause to me, these two colors look very similar. But for the potassium, that's the only one that you put against the black. And if your solution is pretty clear, then you'll see black through it. So then that would make it low. If it's a little bit covered and it's kind of grayish, you'd go medium. If you can barely see the black at all and it's chalky, you've got high.
What's your name?
Anna.
Thank you.
All right.
Yeah, I missed it. I thought it said at least one of each.
Okay.
Yes. Thank you.